Hello friends, in today's question, a slender uniform rod of mass m and length L is pivoted at one end so that it can rotate in a vertical plane. See the figure. There is negligible friction at the pivot. The free end is held vertically above the pivot and then released. The angular acceleration of the rod when it makes an angle theta with the vertical is. So this is the rod pivot point, and rod is making an angle of theta with the vertical, and initially it is said that this rod is in a vertical position. So let us say this is the initial position of the rod. Okay, so this is our z axis and this is our x axis. So this is our initial position, and let us say this is our final position. And here it is having an angular acceleration of alpha. It says that it pivot around this point. So let us say this is having a axis as x and x prime. Let us call this y, because x is already a coordinate. So this is axis through which it is going to pivot with the angular acceleration of alpha. So we are going to have mg in the downward direction, and it can be divided into two components. One will be along the rod and another one will be the perpendicular to the rod. So this angle will be theta. So we are going to have mg sine of theta, and this component will be our mg cos of theta. Let me redraw it here again. So this is our mg, two components. This angle will have a theta, so one is along the rod. This will be our mg cos of theta, and perpendicular rod, this will be mg sine of theta. So this is the rod basically, which is moving in this direction with angular acceleration of alpha. Therefore, we can say that a downward force F, which is equal to mg, is acting at, you can say this will be our center of mass. Now this component can be divided into this force can be divided into two components. This will have two components. First, let us suppose we call this as F1, which will be equal to, this is our F1, and this we say is our F2. F1 we say is mg cos of theta, and this is along the length of the rod. Because of which the torque produced by this force will be equal to 0. Therefore, tau because of F1 will be equal to 0, as, or we can say due to along the line of action. And second will be our F2, which is mg sine of theta, and this will be perpendicular to the length of the rod. and this will be producing a torque. Let us suppose that is given as tau F2. This force will generate a torque. Let us suppose that is given as tau F2, and tau F2 will be equal to a force that is F2 multiplied by the perpendicular distance, or we can say multiplied by the distance between the point of pivot and this. So this distance, the point of pivot, this distance will be given as L by 2 because total length is L. This length will be our L by 2. So we get tau F2 will be equal to force F2 multiplied by L by 2, substituting F2 as mg sine of theta. So this will multiply by L by 2. Now the moment of inertia for this rod along y prime y axis, so it will be rotating about this axis. So this is y and y prime axis, okay, or we can say this will be along the end of the axis. Moment of inertia for the rod about the point of pivot. Let us suppose that is given as y prime, and this will be equal to mass divided by the length and 3. And we also know the torque, which is because of F2, will be given as moment of inertia, that is y prime multiplied by angular rate of acceleration. So substituting the values, tau F2 is our L2 multiplied by mg sine of theta, and this will be m L square divided by 3 multiplied by angular acceleration alpha. Here L square cancel out, mass goes with mass, therefore we get angular acceleration is equal to, this will be equal to 3g sine of theta divided by 2L. So this is the angular acceleration. This is the angular acceleration for the rod, and we check the options which are available to us. So we get this as 3gl sine of theta. So this is 3gl sine of theta divided by 2L. Okay, so option number D will be the correct option. You can say option D is correct. So this completes the question. Thank you.